All right, guys, today we're going to use our logs to model some situations with exponential functions and logs. So just some modeling today. Applications, what we've been doing the last couple weeks. All right, exponential growth doubling time. The formula they're giving you here, right here, is the formula we use to see how long it takes something to double, some kind of mass or some kind of situation to double. N sub 0 right here is the initial size of the population. Doubling time is A. That's the A is how long it takes to double, and T is the size of the population at that certain time. Okay, and T and A must be measured in the same units: minutes, hours, days, years, whatever. Okay. Under ideal situations, a certain bacteria doubles every 3 hours. So we're talking hours. Initially, there's 100 bacteria in a colony. Find a model for the bacteria after T hours. So the first thing, all I want you to find a model. So we're going to say N of T. The initial population is 1,000. We have our 2. And the time, we don't know. But A, it says it doubles every 3 hours, T over 3. And that's the model. Okay, that's all we're going to do right there for our model. Okay, and part B says, so that's A. Part B says how many bacteria in the model after 15 hours. So 15 is your time, so I'm going to put it in 15. That's the T. Just going to plug it in here and do 15 over 3, which is really 5 right there. Just going to punch that right smack in the calculator and see what I get. And got 32,000. Okay, then part C. How many bacteria in a colony after 15 hours? Just did that. Part C. How long will it take it to reach 100,000? So that's this time we put 100,000 this side. Same setup, 1,000 times 2, T over 3. First step right here, I'm going to divide both sides by 1,000. If I divide both sides by 1,000, I get 100. This side over here still got 2 to the T over 3. Now here we go again. When you need an exponent, you don't know it, you got to do log both sides. So I'm going to do natural log 100. Exponent goes in the front, natural log 2. I'm going to divide both sides. I need some more room here. Divide both sides by natural log 2. So I get natural log 100 divided by natural log 2 equals T over 3. Let me punch that in real quick. I got 6.64. If I multiply that by 3, that will give me my final answer. So I get 19.9 hours to get to 100,000. Remember, we're in hours, so almost 20 hours. Okay, next one's exponential growth. This is not doubling growth, it's exponential growth, where things grow exponentially. Here's your formula for that one. When you see N sub 0, that's the initial population. E is just E. R is the relative rate of growth. It'll be some kind of proportion, usually a decimal, and T is time. All right, let's try one of those. It says the initial bacterium count in a culture is 500, and a biologist later makes a sample count of the bacteria in a culture and finds that the rate of growth is 40% per hour, which is, in our case, that's going to be 0.4 or 0.40. Part A. Find a function that models the number of bacteria after T hours. So I'm just going to use this formula right here, the one they gave us on the last slide, to write my formula. The initial count was 500. That was initial population. E, the rate is 0.4. Time, I don't know. That's the model. Okay, so part B. What's the estimated count after 10 hours? That means the time is 10. So I'm going 500. E, I'm just going to put 10 in for T and punch that in my calculator. I want to punch that in. Getting about 27,300. And then part C, when will it reach 80,000? So that's the final amount, 80,000. Starting again with 500. E, 0.4, it's asking me for how long it's going to take. All right, so I'm going to go through there and find out how long it's going to take. So I'm, again, going to divide both sides by the 500. That's going to give me 160 equals E to the 0.4 T power. And because I need the exponent, I'm going to do natural log both sides. Don't forget what happens to the right-hand side. You're just going to get 0.4 T. I'm going to go ahead and put, over here I've got natural log 160. So what I'm going to do to get my answer, my T, is I'm going to divide that by 0.4. See what that gives me right here on the calculator. It gives me about 12.68. So about 12.7. What was that? That hours, 12.7 hours just about to get to 80,000. That population. Okay, let's try one. We're going to compare the two now. This one says the culture starts with 10,000, the number doubles every 40 minutes. Okay, this is doubling, so it means I can use this function. The first one we did, part A says find a function that models it. So I would do n of t. The initial population is 10,000 times 2 to the t over a. Don't know what t is. A is 40 minutes, so I'll just put over 40. That's in minutes here. And then part B, they want you to do the other type of model that we just got finished doing. So I'm going to say n of t. The initial amount again is 10,000. E, this one's the RT. So I need to find the rate here. And because I don't know the rate, I'm going to find it here. So what I know is it's R. That's what I'm looking for. The time is in minutes. So I'm going to say that's 40 minutes is 2/3 of an hour. I'm going to change it to hours. All right, and the final amount's 20. Since it's doubling, it's going to end up at 20,000. This is 10,000 e to the 2/3 r. Divide both sides by 10,000. That's 2 e to the 2/3 r. Remember, I'm just trying to find r here. So natural log both sides gives me 2/3 r over here equals natural log 2. So I'm basically going to do natural log 2 divided by 2/3 to find my r. I'm going to punch that in real quick, and I get 1.0397. Now that's my r. That's not an answer. I'm trying to find my model. All right, so my model would be, now that I know what my rate is, I'm going to say n of t equals the initial amount, e to the 1.0397 t. There's the second model. Okay, and these two models in part A and part B should give you the same answer as you try to find what you're missing. All right, number 7, 2 formulas in this page. If you're dealing with a half-life problem, there's going to be our half-life formula. If you look at it really close, it's the same as a doubling, almost, except for the negative t, and the h is the half-life instead of just, it's half-life. T is time, initial amount, negative exponent because it's decreasing. And radioactive decay is this formula right here, where we got the initial mass, we have E, negative R. R is the rate that is decreasing. T is time. Here's how we're going to find R. That's a big deal. R is going to be natural log 2 over H. And what is H again? H is half-life. I hope you're kind of writing these formulas down. You're going to need them all day tomorrow, so make sure you got these formulas down. Nothing on my slide. Okay. Polonium-210 has a half-life of 140 days. Suppose a sample of the substance has a mass of 300. That's where we're starting. Part A, find a function. Okay, they're asking me to find a half-life function. So the initial amount is 300 times 2 to the negative t over h. All right? We're just writing our function, so I don't know what t is, negative t, but I do know the half-life. Half-life was 140, so there's the function using the half-life formula. Part B wants me to use the radioactive decay formula. So I'm going to do the initial amount, 300 E, negative R, T. So just like the last slide, I'm going to have to figure out what R is. Okay, so I'm going to leave that blank for a second. Something T. So to find R, I know it's going to go into, if it's a half-life, it's going to be cut in half. But remember, they gave me how to find the half-life. And they just said you could just do, and that formula that they gave us was natural log 2 over h. And h is the half-life in response to natural log 2 divided by 140. Punch that in your calculator, natural log 2 divided by 140. And this looks like it's about negative 0.00. And it's going to be negative every time, 495. So I didn't leave myself enough space. So my second formula, part B, 300 times e to the negative 0.00495 t. All right. Then part C, find the mass remaining after 1 year. Now you can choose, I guess, whichever method you want to go here. You can use part A or part B to find part C. But after 1 year, now remember these are days. So 1 year is 365 days. So let's use the first one. Okay, so I would say the amount left after 365 days would be 300 times 2 to the negative 365 divided by 140 as my power. If you punch all that in, you get about 49.256. Was this grams or what? Yes, milligrams. That's how much is left after 365, after 1 year. Part D, how long will it take to get to 200? So here we go. I'm going to use the same formula, except this time I know the final amount. So I'm going 200 That's the final, starting with 300. I don't know my t, divided by 140. Divide both sides by 300. I'm getting 2/3 over here. Is 2 to the negative t over 140. Out of room again. Let's see here. Move this up. There we go. So to finish this one, I'm going to do natural log of 2/3 equals negative t over 140. Natural log 2. That's a t on the numerator, by the way. So negative t over 1, sorry about all this time, is going to be this divided by natural log 2, and then times 140. Okay, somebody came in the room. I'm not sure where I was there. So just going to finish this real quick. Going to punch it in. I'm punching in natural log 2/3 divided by natural log 2, and then times negative 140, because that's going to give me my final answer here. When I punch all that in, I'm getting 81.9. All right, so that's how long it would take. And again, this is in days. This is going to take almost 82 days for it to decrease from 300 to 200 milligrams. Guys, I know that's a lot, and you're not used to watching a video of all applications and formulas and word problems and stuff like that. We'll do several of them in class like we always do. You'll be fine. If I were you, I'd go back, make sure you have these formulas down. You need to write them down so you know what to use on which problem. That's going to be the biggest deal. Like, figure out what the problem is and do that kind of formula. Okay, so I'll see you tomorrow.